okay? So there's more than one way to create a sigma bond. And this is where this can get a little confusing. So to make a sigma orbital out of anything but H2, we technically need 2s and 2pz, or even 3s and 3pz, or 4s and 3pz, and so on and so forth, okay? So H2 is literally the only thing that we can make a sigma bond using 1s electrons. Everything else, it's got to be higher order. So now if you look at, so this is the 2s and the 2pz superimposed. And I'm going to do the same trick here, right? Where I've got atom A and atom B. And we're going to make them scale in and out of each other. Well, if you look at the complete basis set for this, okay? Right, we've got some normalization constant times the wave function for A2s and B2s and A2pz and B2pz. We can actually separate these into two separate basis sets. And again, following the LCAO-MO, the linear combination of atomic orbitals, because we don't know which is which, we get this plus minus state. And so we're going to call linear combinations of 2s also the 1 sigma g and 1 sigma u. We note that hydrogen is the only one that has 1 sigma g and 1 sigma u from linear combinations of 1s wave functions. Everything else is linear combinations of 2s wave functions, all right? And so this plus or minus state will create the 1 sigma g and the 1 sigma u, bonding and anti-bonding. But now, what if I combine 2pz? Okay. Well, hopefully what you remember from the valence bond theory, when I orient 2pz orbitals towards each other and they combine, they make a symmetrically cylindrical electron density about the internuclear axis, right? So here is my z-axis once again, and there's my nuclei B, and there's my nuclei A, and I even have this down here on my model. Let's find it. Let's see, here we go, right? So here are two p orbitals, right? So you can see in this case, they're oriented on that z-axis. And now, as I get them close to each other, they create this enhanced electron density in the internuclear zone. So that is also a sigma bond. You also notice there's electron density on the outsides right there. And typically, those are where lone pairs can exist, okay? And so now, if I consider my symmetry operations here, right? So I drew my z-axis. So we note that when I combine A plus B, okay, and I look at this symmetry operation, that's going to have Girard symmetry, which is why we call it the 2 sigma g. But now what about the anti-bonding? Well, so here I've got the anti-bonding model for 2 sigma. And you notice here now when I try to get those close to each other, once again, that anti-overlap integral really takes over and pushes all of that electron density out to the other regions. And of course, the more they overlap, the more that positive and negative will cancel each other out, owing to an anti-bond. So when I do a symmetry operation here, and again, nuclei B and nuclei A, there's a change of sign when I cross that center of inversion. So that means the anti-bonding for 2 sigma also has un-Girard symmetry, okay? So when we combine 2s and 2pz, we get 2 separate basis sets. We can make a 1 sigma g and 1 sigma u out of combining the 2s. And we can make a 2 sigma g and a 2 sigma u out of combining the 2pz. And of course, the plus state will give us bonding, and the minus state will give us anti-bonding. All right, so continuing along. So here's some pictures from my, like I said, from my Gen Chem notes, which you can see in the simulations, but just to summarize, to go through this, right? We can make sigma bonds from all of the following: a 1s plus a 1s to make a sigma 1s bond, and I'll note that that's called the 1 sigma G. Okay. If we do the minus state, a 1s minus a 1s, we know that that makes the sigma 1s, which sigma 1s star, which we could also call the 1 sigma U. All right. And then of course the same is for 2s, so I'll just say same for 2s linear combinations. They still make what we call the 1 sigma G and the 1 sigma U. When I make linear combinations of 2pz and 2pz, I make the sigma 2p bond. In Gen Chem, that's what we would call it. The more correct name would be 2 sigma G. And of course, I can make this antibond just like I showed you from subtracting these. I could call it the sigma 2p star in my Gen Chem book, but the more correct nomenclature we use for spectroscopy, 2 sigma U. Okay.